Number 4, final lecture. All yours.
All right, test. Oh, test, great. Yeah, great. Sorry, just making space. So yeah, so tropical Chabauty. These are pictures that Joe Rabinoff made that I will explain when relevant. So as before, quick recall, slide -1. This is a photocopy of a slide from my first lecture, essentially. So the theorem that we spent the first few lectures discussing is Lorenzini-Tucker, and McMinnon, and then our improvements and Stoll's improvements with the 2R. There's the running rank less than G hypothesis, which is essential, and there's this P greater than, that's an R, 2R plus 2, which is less essential. That just changes the kind of local term. And the big feature that, so the Jacobian was the enemy. In this case, regular models are our enemy. The issue, and I'll explain with the picture in a future slide, is that this quantity can be arbitrarily large. So if we're trying to find realistic or sharp bounds or prove something uniform, the regular model, while it has a lot of utility, is a problem. So what I want to discuss today are the following 2 theorems due to Michael Stoll and myself, Eric Katz, and Joe Rabinoff. So Stoll had the bold idea to work with a stable rather than regular model, or at least take a regular model, and the failure of finiteness is you get chains of P1s, and so he contracted the chains of P1s. The expense of this is that he needed to work with hyperelliptic curves in order to get explicit bounds. One upshot of hyperelliptic is you know what differentials look like explicitly on a hyperelliptic curve, and then it'll take some work to explain this, but he needed some extra flexibility in the space of annihilating differentials. So he needed at least a 3-dimensional space of annihilating differentials. And then I was at a conference with Eric Katz in Colorado, and it was one of those 20-minute by 20-minute special sessions where every 20 minutes we would read a little bit more of Stoll's paper until we figured out that we could use tropical geometry to kind of generalize his theorem to the general case. So I'll talk about KRZB this lecture. And then just really quick, another photocopy from last time. Recall that a scheme is regular if the dimension of its Zariski tangent space is equal to the dimension of x at that point. For every point, this works over spec of z, and it's an absolute rather than relative notion. For us, one upshot of regularity is that it implies that the image of the reduction map is contained in the smooth locus of the special fiber. So in this theorem of Lorenzini-Tucker, in a sense, there's some setup cost in terms of what integration means, but once you sort that out, Lorenzini and Tucker's proof is essentially the same as Coleman's proof. You work residue disk by disk. So that's why we have regular model. And in fact, by Hinsel's lemma, every smooth FP point lifts to a QP point. So it's an equality in this case. So I'm obligated to write. So as I said before, the problem is that Eek's smooth FP is unbounded. So example, if I take, I mean, there's nothing that special about this example. It's just a short equation and easy to draw the picture of. So in characteristic 0, this is an elliptic curve. In characteristic P, I'm going to leave some space here. Mod P, you get 3 lines, x, y, z equals 0, and then some kind of tilted elliptic curve. And then if I decorate this, so with just the power of P here, this is regular. The local equation at each node is, so now I want to write this. The local equation is x, y. Okay, so if I'm working mod P, what does it mean to be transverse? It means the local equation is x, y equals 0, maybe over the algebraic closure. And then if you're working over ZP, this condition is the local equation is x, y equals P. And then, so this is regular. If I put P to the n, the local equation is x, y equals P to the n. And this is not regular. So to attain a regular model, you have to blow up. Don't say that in the airport. Ask Tony Verily about that. I like to say inflate. It's more like you're adding balloon animals to your curve. And so when you inflate, you get, instead of an n-gon, in this case you get a 3n-gon. This n specifies the number of blow-ups, or maybe it's a 3n minus 1 gon. The number of blow-ups you need, and each blow-up reduces the power of P appearing in the local equations at the nodes. So it's fairly explicit, but you can see that even in this example of an elliptic curve, the special fiber of a regular model could have arbitrarily many P1 components. So in these proofs, this is what I mean by this might be unbounded. On the other hand, if you have a regular model, you could conceivably contract any chain of P1s like this, where by chain, I mean each P1 intersects exactly twice. It's semi-stable, but not stable. When you do that, it's no longer regular, and points might reduce to the nodes. So, great. So again, Stoll's idea is to work with, well, in general, a stable, but I'll just say non-regular model. Contract chains of P1s. This implies that now ex of FP is bounded. Okay, well, bounded in terms of what? Via, let's just say, P and the genus. But then the problem is that now, I'll basically spend the rest of the lecture explaining why this is a problem and how to fix it. The setup and the local analysis, so like the Newton polygon part of the argument, is hard or difficult. So, all right, so I'll skip to the punchline. My idea with Eric, and then later we recruited Joe Rabinoff because he knows a lot of good technical details. He's really the expert for these things. Our main tool is, and this is, so Katz, Rabinoff, Zureick-Brown, they'll phrase it as the systematic use of Berkovich and tropical geometry. So here are the issues in a black box for how we solve them. Then I'll explain Berkovich spaces and the tropical tools. So the setup step, which in my first 2 lectures was simply that there exists a space of annihilating differentials that are locally analytic, is trickier. So the problem is there are 2 types of integrals. There's what's called the abelian integral and what we call the Berkovich-Coleman integral. And the difference is this abelian integral comes from the Lie algebra of the Jacobian. So it's like its profile. And this is the integral that annihilates rational points, for nice omega. On the other hand, in the bad reduction case, this abelian integral is more difficult to explicitly compute unless you're working in a residue disk. On the other hand, the Berkovich-Coleman integral is more computable, but generally not equal to AB. And so the initial version of our paper before we recruited Joe, we were simply thinking about how to compare these integrals and make things line up. And then we realized once we did that, we could get uniform bounds. So Stoll's theorem from the first slide, his big observation is that while these integrals generally differ in the bad reduction case, the difference is linear in the input omega. And so if you have a two-dimensional space of annihilating differentials, you can pick an annihilating differential where these match up. Side note, he discovered this by computing hundreds of thousands of these. No one else had tried to do that. I just assumed, and I assume others in the field had, that there was just no hope of comparing these and that it wasn't really worthwhile to consider this, but he took the bold step of computing examples and noticed a pattern. Then what Eric and I noticed, by which I mean what Eric noticed in Utah, or in Colorado, was that I'll phrase this in a fancy way, but I'll give a concrete example. The difference factors through trop of t, where this t is the following. The Jacobian has either a rigid analytic or Berkovich analytification. And then Raynaud, Eric likes to call this the Raynaud uniformization cross. So you have in the Berkovich sense, the universal covering space in the literal sense of first-year algebraic topology. There's a period lattice. This surjects onto an abelian variety with good reduction. And then the kernel of this surjection is some torus. So in the case of, say, a curve with good reduction, you just get the A with good reduction. In the case of something like a Tate curve, you get the T. And then in general, you get a mix of these. And so that T is kind of where the difference between these integrals lives. And remember, trop T, it's a torus, so it's just a big sum of, a direct sum, right, product of GMs. So this trop T is really, let me put this back on video, this trop T is really R to some power. But it's the plot, the closure of the plot of p-adic valuations. And then it gets better. Okay, that's just the setup, and I said the local analysis needs improvement. So we use what I like to call the fundamental theorem of tropical geometry. And part of that is what I'll just call potential theory on the Berkovich analytification. And then the Riemann-Roch step, so I'll call this global step, or global coordination, really there's somehow some combinatorial optimization. So Eric was before in a combinatorics department at Waterloo for sections of the tropical canonical, or rather for zeros of bundle. And so we really need the continuous version of this, but the discrete version, so a toy version. Fun to think about. From last time, if you take the dual graph of the special fiber, its canonical divisor, and then some d in that linear system. So this d is effective and equivalent to k. By this combinatorial optimization in this discrete case, the problem is to bound the minimum number, so it's like a min-max, of firings, so lendings and borrowings, to witness, or which witness the equivalence k. So the subtlety in this is if you fix the genus, it's true that the homotopy type of the graph gamma is bounded, but you can still take any graph and subdivide. So you can have arbitrarily many edges if you allow vertices of degree 2. And so it doesn't just obviously follow from some fact about eigenvalues of matrices. And in fact, we couldn't really just solve this discrete problem without introducing the continuous part. And then I left off rank favorability because we don't know how to do that yet. We've tried. I had my master's student, Noam Cantor, try, and we're out of ideas. So next, we are time travelers. Let's yeet back to 2007. This is rigid and non-Archimedean geometry. Let's have a quick review. The Gelfand spectrum, this is the analog of spec, is the collection of norms, or rather bounded multiplicative semi-norms. This has a topology because given a norm, there's an evaluation map to R. I'll call it EVF, but which sends a norm to evaluate your norm at F. So you put the smallest topology, which makes these maps continuous. And you can write down certain types of norms. Actually, one quick comment. If you have some point in this spectrum and you have some element, so really it's a function on your field, we write, so we'll do this later, things like f of x. And this is a little in the same way that in scheme theory, when you define the beginning of Hartshorne chapter 2, you define closed subsets. There's this bait and switch. Well, you evaluate a point at x, but you really do something where you map f to the residue field and see if it vanishes. Here, the point x is a norm. And so when I write evaluate f at the norm, I really mean this. So it's backwards. Anyway, that will come up later. And as an example, first let's let QP braces T. This is the ring of convergent power series on the p-adic unit disk. So an element is a power series, 0 to infinity. AI is in QP, but most of them are not. The p-adic valuations go to infinity, so the norms go to 0. So these converge on the unit disk. And then the Gelfand spectrum. I'm only going to do really 2 examples of this. That's a T. So first of all, like in scheme theory, spec of a ring contains the closed points. Here, this contains the points coming from essentially ideals. So it contains max spec. This is true for any R, T. So let me explain. If I have a point of this, or really just a point of ZP, or really ZP bar instead of QP. But just think of ZP a disk. then there's an associated norm, which is when you evaluate this on f, you just plug in x. So there's, in the same way that points of a variety give you maximal ideals, here points of the p-adic unit disk give you a norm, which is simply evaluate at the point and then take the p-adic valuation. On the other hand, this is much larger. So the p-adic unit disk is totally disconnected. You can check there are no continuous non-constant maps from an interval. Sorry. On the other hand, the Skelfon spectrum in this case is a in fact, contractible Hausdorff topological space. It looks a bit exotic, but it's fairly concrete, at least in dimension 1. So I just want to say there are more points. So here's ZP, but there are more points. For instance, there's a norm, which when you evaluate on F, I'll call this norm B, or really B. So here, I mean take a point X and a disk of radius R. And this is the sup norm. So essentially take the max of for X in this disk, evaluate F at X, and take its p-adic evaluation. So let me redraw. So we draw this picture of the p-adic unit disk because, well, it's kind of a disk. But this is really, we joke about cartoons. This is really a cartoon. This Berkovich space, the true picture is the points I drew here kind of live out at infinity. And then if I pick, let me just call this one A and B, 2 points A and B and the disk, you can, so these points correspond to a norm from this previous slide. You can connect them by taking, well, a disk of radius 0, that's just the point, and then larger and larger disks until you get one which contains both, and then smaller and smaller disks, so we can kind of connect them. And so you end up getting this tree. And in fact, topologically, this is, the topology is almost the topology of the picture that I just drew in the plane. Well, it's really an inverse limit of the tree topologies, but it's essentially just a tree. And this shows you that it's contractible too. You can see, I mean, this is really the true picture. I mean, you get uncountably many points, but then they're each uniquely path connected, and they contract to this point, which is essentially you take the disk of radius 0. So the upshot is that this is a Hausdorff topological space. It's path connected and locally path connected. It does have this fractal-like structure, but it's fairly computable, at least in small dimensions. And there's lots of stuff you can do with it. So let's do one other example. Remember that the local equations for a node look like x, y equals p to the n. I claim this is an annulus. So look, if you specify x, you can solve for y. Neither x nor y can be 0 because of this equation. And then you have an upper and lower bound on the valuations of x and y. That's an annulus. On the other hand, the Berkovich picture looks like this. So I have a smallest radius disk and a largest radius disk. And then the disks emanating outward, centered at the origin, give you an interval. But then the actual different points still kind of live out here. And I'll draw the best picture I can. If I pick a point over here and I eventually let these disks shrink around it, you get a path connecting these. So this is a Berkovich disk. and a Berkovich annulus. So one thing that can be a bit confusing is both of these are contractible. On the other hand, we're used to the fact from scheme theory that the topology doesn't determine everything. Topology is useful here. For instance, two curves over fields of the same cardinality are homeomorphic regardless of what their genus is. They have the same cofinite topology in the Zureick topology. So really, there's a bit more. You can globalize, so you can glue. And to glue, you need sheaves, and these have cohomology, et cetera. And so one difference between the disk and the annulus, even though they're both contractible, is that, okay, this has trivial de Rham cohomology, this has non-trivial. There are some differentials here that are, you phrase differentials in terms of sheaves. Some here that are non-exact, but everything here is exact. And these are theorems that you have to prove and check. But these have different sheaves of rings, just like curves in scheme theory. The gluing part isn't exactly trivial. This gets very technical. There's a business of nets and so on. But we don't need that since we're only working with curves today. So that was 2007. It's 13 years later. And we now have what I like to call, so for classical Chabauty, before we use the fundamental theorem of calculus, here we will use what I call the fundamental theorem of tropical geometry. Which, to be fair, this is just a collection of everything I need from tropical geometry. Therefore, it's my fundamental theorem. So this is clearly summarized and slightly improved in this famous paper of Baker, Payne, Rabinov, which is really the best starting point for this. But the original work is due to Berkovich. And for the potential theory part, this is Toulier's thesis. So let's take an X over ZP, which is semi-stable, and guess what example I'm going to draw. So the really neat thing about all of this is that it is incredibly explicit. So again, the special fiber looks like a three-gon. I guess this is X FP. The generic fiber is X QP. And then I want to show you what X an, or I mean the Berkovich analytification, looks like. I can't really define this in this lecture, but locally, preimages of smooth points are disks. Preimages of nodes are annuli, and this gives you kind of a pair of pants, in the Berkovich sense, decomposition. Let me at least draw the picture for you. Hey, actually first, there's one more type of evaluation I want to talk about. So if I label these components C1, C2, be careful, C3, then there's a valuation which takes a function on the generic fiber, extends the function to the model. Now, if you do that arbitrarily, you might it might vanish identically on the special fiber, or it might have poles identically on the special fiber. But there's going to be some power of P, or your uniformizer, such that it doesn't vanish identically. And of course, if you have an extension, you can just multiply it by P, and that function vanishes identically. So there's one P which is just right. On the other hand, it still might vanish along one component, but not the other. We'll do a very explicit example after this. So there's a valuation which is send F to the valuation of the function F along the component Ci. So by valuation, I just mean do this dance with the power of P so that it doesn't vanish identically. And then if it vanishes completely along C1, record the order of that vanishing. So in the Berkovich space, this gives us 3 points. So 1 for each component. I have to label these. So the left component, I'll call it V2. The right component is V1, and this is V3. Okay, great. So we're constructing the dual graph via this Berkovich theory. That's what these vertices are, these valuations. And then these two components meet in a node. So we said that's an annulus. So let me color these pink. So we get pink, 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 but then a bunch of Berkovich stuff coming off of this. And then these smooth points along this component, these are disks. So we have a disk here, here, and then here, and avoid the V3. And, well, aside from the fact that it's infinite, this is actually an accurate picture of what the Berkovich space looks like. So the fundamental theorem of tropical geometry is that there exists an embedding of the dual graph of the special fiber into the Berkovich space. Maybe there exists one, and there exists a contraction in the algebraic topology sense, tau. You can see the contraction onto the dual graph from this picture. The blue and the pink fuzz just eats to the dual graph. So it's even better than this. This contraction is compatible with reduction. And this contraction is the surjection. Compatible with reduction in the following sense. So what did I constantly do in the previous lectures? I took a point of the generic fiber and I took its closure. So here's a green point that I'll call A. Well, A lands on the component C2, and it's an actual point. It's not one of these norm points coming from a ball or a disk. And in this picture, this lives out here. So the way to read this is, if this reduces to, I mean, this is really some point here. This is still a subset. If this reduces to this component, then it contracts to the vertex corresponding to that component. So if I have this blue point reducing to a smooth point of C1, that lives out here and then contracts here. And then finally, this is not necessarily a regular model. If I have a point which reduces to a node, so this is C1, C3, so C1, C3, great, then it doesn't contract to V1 or V3. It contracts, let me call this C. It contracts C, B, A, to somewhere along this edge. And I'll just say the location along this edge that C contracts to, you can read off of how many times you have to blow up or inflate this model before C reduces to a smooth point. So there's some number of blow-ups which kind of resolve the singularity of the purple curve intersecting the node. So there's really a very explicit recipe for this. One more thing, this dual graph is now no longer just a discrete graph. I mean, I'm really using the topology here. It's a metric graph, and you can read the length of these edges off of the local parameters. So in this example, the power of p in these local equations, when you write it, excuse me, is xy equals p to the I, of course, tells you the length of this edge. In this case, they're all the same power of p, so it's equilateral. So this is part one. This is Baker, Payne, Rabinoff's paper is titled "On the Non-Archimedean Structure of Curves," I think. And then I promised some analysis. So let's do potential theory. So it might be theory. Suppose you have just some map to P, or analytic or algebraic function on the Berkovich space or some subset of it, like an integral, and you would like to understand the zeros of that integral. That's what we want to do in Chabauti's method, understand zeros of integrals. Let's take an algebraic function for now. Then you can discretize the function. So I'll say f. So I said what f of x means before. This is the p-adic valuation. So given a function on the Berkovich space, we can take log of absolute value of evaluate f on the point. And if you start working examples with this, we'll do one, it becomes completely clear that f restricted to the dual graph, so we call this the skeleton, is piecewise linear. We'll do an explicit example. And then the theorem is if we take div of f, so again, I want to count zeros, and we contract this to the dual graph, that this is the same as this combinatorial div of capital F. So I'll define this to be, I said this was piecewise linear on the skeleton, but it's not linear, and anywhere there's a break, you have incoming slopes at that point. So you define this to be a divisor on the graph, where at a point P on the graph, the number, the multiplicity you put is the sum of the incoming slopes at P. So this is a divisor no longer just on the vertices, but it might be supported somewhere along an edge as well. So this tells you, this is the analog of Newton polygons. I should say in the case when X an is simply a disk, the thing I wrote down is literally Newton polygons, but you have to work that out for yourself. And then in general, this is kind of like you compute this using Newton polygons, except that this graph might have, say, vertices of degree 3 or 4. So it's kind of like emanating Newton polygons in different directions. Let's do one example. Otherwise, this is unbelievable. And I want to say this is this is the tool we need to do the local analysis. We turn analyzing zeros of something into a combinatorial question. It's like Newton polygons. Let me make a new page for the example. This is 7. So here's the simplest function I can possibly write down. So same example, take f of a projective point. I should have put, there we go, projective point, to be just x, z. So it's the x coordinate map. Projectively, you send xyz to xz. But it's on this example, the xyz equals p times stuff. What is div of f? So we're looking at zeros and poles. If x is 0, you're solving y cubed plus z cubed is 0. These are 6 roots of unity. So this divisor is going to be 0, zeta 6, 1, plus 0, zeta 6 squared, or cubed 1, etc., minus, okay, if z is 0, you get x squared plus y cubed is 0. The p doesn't matter. We're solving this in characteristic 0, and here you get 1, zeta 6, 0, plus that. So div, let's draw the picture again. You have to be very careful. So I'm going to label this line y equals 0, this line z equals 0, and this line x equals 0, x, y, z. Great. And then the Berkovich picture again is this with a bunch of stuff coming off. Great. Let me draw a picture of div. So the positive part of div reduces to, I guess p is not 3. The positive part reduces to 3 points on the special fiber with coordinate x equals 0. So maybe the points are here, here, and here. And then the negative part lands on the z equals 0. So this picture, which I forgot to say, Joe's picture, Joe Rabinoff, I don't know what he used to make this, but this is just a the color coding represents the same thing as my color coding here. So these pictures are from our Utah survey. So in this picture, we said that these 3 points, 1, 2, 3, they're smooth points of this vertex, which is here. And so they live, I need an extra branch, out here. So when you contract them, you get a point here with multiplicity 3. That's this div. And then these 3 blue points live on this component. So they live out here. And when you contract them, you get -3. So here I computed, let me just redraw this. On the skeleton, or dual graph, we computed that tau lower star div of f is the divisor 0, 3, -3. Okay, that was easier than this. For the potential theory part, let's now graph f. Except we're graphing f over this triangle. So, all right, moment of truth. Here's a triangle. I'm going to write the graph above. I'm going to do the best job I can. I'm going to say this is the value 0. Here's 1. Here's -1. So I'm going to draw the graph above the triangle. And let's start at x equals 0. Along the line x equals 0, mod p, this function has a simple 0. The function is just xz. So the vertex, this vertex, remember, the point of the Berkovich space that this vertex is you take f and you evaluate, you take the order of vanishing along here. So which is to say, I can explain this more afterwards if this isn't clear, that the value of this function here is 1. Similarly, this function does not vanish along y equals 0, so the value here is 0, and this function has a simple pole identically along z equals 0, so it has value -1 here. And so if you connect these, you get slope 1, and then slope 2. Okay, you have to think a bit about why it's linear from here to here, but essentially it's just an annulus. I mean, you actually have to do some computations and maybe write out power series if you like, or soups. But if it's, yeah, okay. So anyway, you have to check that it's linear here. And then what do I mean by div? So the sum of incoming slopes. Here, the slopes are 1 and 2, so you get a 3. Here, the slope is 1 and -1, or rather, the incoming slopes are both 1, so you get 0, and then here you get -3. Okay, so this is a computable example of potential theory on Berkovich curves. And again, note how explicit this all is. Okay, so that's the tool. I'll say one more quick thing. I said we needed a slight generalization of this. So one thing we do in KRZB is if we have a metrized, so a line bundle, a section, and a metric, so this is kind of what happens with the canonical sheaf, then we have an analog of the slope formula. So same formula. So div of the section is div of f, where f is minus log s. But then there's an extra term. This is kind of like Riemann-Roch, and it's just, if you like adelic stuff, it's the volume with respect to that metric of L. So kind of one part of the global step is a formula like this. It's only a mild generalization of their work. So, great, so there it is, metrized line bundle. Quickly, this is the name of my new metal band, Axioms for Integration. Integration on a Berkovich space works like the following. X-an is a Hausdorff path-connected, generally path-connected, locally at least, space, and what we do is we set up axioms for integration. So we want a pairing between paths. Okay, well really, we can only make this work for paths whose endpoints are type 1 points. Pairing between paths and differentials valued in CP, which is locally analytic, so same as before, on a disk or polydisk, if omega is exact, so it is on a polydisk, then the integral is given by endpoints. Now here, I really mean gamma is a literal path on the Berkovich space, and just like calculus 3, you compute it like this. An improvement over what happens with rigid spaces is that this integral only depends on the homotopy type of gamma, and it's linear in composition of paths, omega, etc. And the really neat thing is that there are still choices that you can make. So this does not uniquely determine the integral. So my favorite example is if you take Gm, here's a non-exact differential on Gm. Gmn is an annulus. It's contractible, but this differential is not exact. And this integral should be log of t. Now, we know from graduate algebraic number theory how to define log. So here's Cp, OCp star, OCp1. Here you use the power series from calculus 2. Here, it's a group homomorphism, so that's a root of unity. So you can extend it to OCp star linearly, but then there's still a choice. You must choose log of p. So there's ambiguity, and really I should write something like Berkovich-Coleman here. There's not a single integral, there's monodromy, or if you like, there's some ambiguity in how you analytically continue. The annulus is still covered by disks, and each disk you can integrate this way. But somehow when you piece that together, you get a choice. Either you make a choice of log of p, or if you construct an integral in some other way, that imposes a choice of log of p. And then Eric's naive but ultimately correct observation was that this choice of log of p really, or somehow, so Cp star mod O of Cp star, when you take the closure, that's R, which is trop of Gm. And I'm still surprised that this generalizes to the general picture. So in the final, we started 2 minutes late, so in the final 4 minutes, what I want to say is, let me cover up most of this slide, is we haven't used calculus 3 yet. Technically, Jen was using this. So I'm teaching an honors multivariable calculus course. It's kind of like Math 55 at Harvard, but a tenth of the material, so I call it Math 5.5. And so I taught them right before the winter school about functoriality of integrals, which is if you pull back a differential and integrate along a path, that's the same as pushing forward the path and integrating omega along the push forward. And actually, I claim this is what we were already doing. When we integrate on C via the Abel-Jacobi map, well, an integral on C is pulled back from the Jacobian. So in this language, for the abelian integral, you define it by pushing to the Jacobian. And then this business where you push to a residue disk, that's functoriality of the multiplication by n map. So the abelian integral, the one that you use to annihilate rational points, comes from applying functoriality to Abel-Jacobi and Jacobian maps. On the other hand, you can't always get what you want, and you can't simultaneously require functoriality for every map. So alternatively, this is an intentionally fancy version of essentially what Jen has been talking about in her lectures. So it's a theorem of Coleman, Deschely, Berkovich, and Dwork, although we rephrase it and make sure everything works in the Berkovich space, which is that if you fix log of p and require functoriality for instead the Frobenius map, then this choice of log of p, or maybe for each disk a choice of log of p, uniquely determines an integral that we call the Berkovich-Coleman. And the Berkovich-Coleman integral does not annihilate rational points on certain differentials, but it's computable. The axiom we wanted was that integrating exact differentials is given by the fundamental theorem of calculus 1, just by the endpoints. This took us a lot of time to sort out what was going on. It's Berkovich-Coleman integral. The point is, if you have any open subset of the Berkovich space, an annulus, a wide open even, and an exact differential, not every differential on the annulus is exact, but some are, then integrating is given by plugging in the endpoints. So for the abelian integral, this only holds on disks. The Berkovich-Coleman integral, this desired property from Calc 3 holds anytime you have an exact differential on a wide open or annulus. So in particular, this gives us a way we can compute the Berkovich-Coleman integral, but the thing we want to compute is the abelian integral. In general, these disagree, but my first axiom, so to finish, my first axiom was that this should be linear in omega, that it's path independent. So there's this numerical theorem of Coleman, which is that if x has good reduction at p, this is an analyst paper, that these two integrals agree, i.e. it's independent of path. The proof that we give in our paper is directly just that the Berkovich space is contractible in the good reduction case. The special fiber is, or the dual graph is a single point. And I wanted to comment, so again, so functoriality for Frobenius, this is kind of one of the steps Jen was using. And then just finally, last slide, final remarks. Sorry to switch away from writing, but I really wanted to say this. So to put this all together, why are at most 3? So in Stoll's theorem, he proves that the difference is linear in omega. So if you have a two-dimensional space of differentials, then you can find a differential where these agree. So this is what you want to compute. And if you have at least 2 dimensions worth of differentials, you can compute it locally using Berkovich-Coleman. But then we want to work on annuli. A regular model can have arbitrarily many points. A stable model might not. A differential on an annuli is close to exact, but there's a residue. So if you have 3 dimensions worth of annihilating differentials, you can kill off the residue and compute exactly. So this is, so we give a more, conceptual via Berkovich spaces proof. And there's still a lot of, the paper is still long after that part. One comment is to prove something like what we prove, you still have to use other theorems from tropical geometry, like the Jacobian of the tropicalization is a tropicalization of the Jacobian. Some of this compatibility relies on some pretty technical and important theorems from tropical geometry. So that's all I wanted to say. Thank you.
Any questions?
Nitan?
So can you say something about how the differential you need to choose to annihilate this differential, to annihilate this residue, to make the residue be 0, how it changes when you change the annulus you're on?
Great, so I can say that it changes. Full stop. But in this picture that I conveniently put up, if instead of taking the preimage of a node, if you take a preimage of a component, you get a pair of pants, meaning for each node you get a puncture. And so in this example, there are 1, 2, 3 punctures. I guess I wanted 4. So there are 4 punctures. And so to work on that wide open, that preimage, you really need, instead of G minus 3, G minus 6. And that's just a fact of life. So I don't, this is maybe part of the problem with the rank favorability as well. I don't know how to coordinate the residues at the different annuli. Of course, there are these theorems like, from Riemann, that if you're on a Riemann surface, then the sum of the residues is 0. But, yeah. So Bryden. Thanks for waiting.
Is the reason that you associate, or an annulus is associated to a node, is this because if you take a smoothing of a node locally, it's really is topologically an annulus?
This is
version of that?
So morally, yes, but this is so. The question was essentially, why is a preimage of a node an annulus? So morally, yes, it's because of the smoothing, but this is fairly explicit. At least after a small extension of the residue field, the local equation for the node is xy equals some power of p. You can just write out the powers. So it's an analytic isomorphism. You can just write out that whatever analytic coordinates give you xy equals p, those analytic coordinates, so p-adic analytic, give you the isomorphism with the annuli. It's really that computation I did earlier. It's xy equals p. Or p to the I.
Okay, let's thank David again, and since this was his last lecture, let's give him a big round of applause.
Okay. Okay, great. Hold on. In that case.
We resume at 11:30, is that right?